Hello sir, hello classmates. So in this video, I will create a program implementing binary search tree. So first, let's create three classes. So the first class we need is the main class. So this is where the binary search tree class will be instantiated. Next, we will create a class for the binary search tree. So this class implements the binary search tree. Next, we need a node class. So this class represents the nodes of a binary search tree. So a node can have a value. So let's declare an integer variable called data. In addition, a node can be a parent node or a leaf node. When we say leaf node, it doesn't have children nodes. While a parent node, it can have a maximum of 2 children nodes. Either way, we still need to create 2 node objects for the children nodes of our parent node. So one is called left and one is called right. So after that, we need to create a constructor method for the node class. So a constructor method will be executed once we instantiate our class. So once we instantiate our class, we want to assign data a value. So we want one parameter. So let's name it data. So this keyword signifies that we want to access data variable from the node class. So these two variables are different since this data is from the parameter. So let's head back to our binary search tree class. So a binary search tree has a root node, so let's create one using the node class. And since we are implementing binary search tree, we need some methods. So let's start defining the insert method. So it needs one parameter, which is the node to be inserted. Since we are doing this in a recursive approach, we need a helper method for our insert method. So let's define our helper method. It has a return type of node and let's call it insert helper. It needs two parameters, which are the root node and the node to be inserted. So inside our insert method, we will call our insert helper method and assign the value that it will return to our root node. And we will pass in the root node and the node to be inserted as the arguments. So inside our insert helper method, we will create an integer variable that holds the data of the node to be inserted. So let's call it data. So before inserting the new node to our binary search tree, we will first check to see if our binary search tree is empty. So we can say that our binary search tree is empty if our root is equals to null. If it is, we will assign root with a new node and we will return root. So else, if our binary search tree is not empty, we will check if our data if the data of the new node is less than the data of the root node. So if it is, we will recursively call insert helper and assign it to the left child of the root node. So that is root.left. So we will pass in root.left or the left child as the root node and the node to be inserted. So else, if our data is not less than the data of the root, we will recursively call insert helper and assign it to the right child. So after that, we will return root. So next, we will define the in-order traversal method of the binary search tree. So in-order traversal method traverses through the binary search tree in order. So it will traverse the left child of the root node first, since left child will always be less than the root node. Next is the root node. After the root node is the right child, since the right child will always be greater than the root node. So let's create the in-order traversal method. So it takes no parameter, but just like the insert method, we will still need some helper method for our in-order traversal method. So let's create one. Let's just call it in-order helper. So this method takes one parameter, which is the root node. So inside our in-order method, let's call our helper method and pass in our root node as argument. So inside our in-order helper method, we will check to see if our root is not equals to null. If it is, we will recursively call in-order helper. So we will first pass in our left child. So this line of code traverses through the left child recursively. So after that, we will print the data of the root. After the root, we will again call in-order helper recursively and pass in the right child. So let's head back to our main method or our main class and instantiate our binary search tree. So let's try inserting some values first. So since insert method takes node objects as parameters, we can also pass in anonymous classes as arguments. So let's try inserting numbers that are not in order. And let's try calling the in-order traversal method. So as we can see, the nodes of the tree are printed in order. So the next method that we should define is the search method. So this method returns a boolean value. and it takes one parameter, which is the data that we want to search for inside our binary search tree. And just like other methods, this method needs a helper method, since we will search for data inside our tree using a recursive approach. So this helper method will return a boolean value, and it takes two parameters, which is the root node and the data. So inside our search method, we will return the boolean value that search helper will return inside our search method. So we will call search helper inside our search method, and we will pass in the root node and the data as arguments. So before checking for the data inside our tree, we should check first if our tree is not empty. So we can use the same condition, which is root is equals to null. So if root is equals to null, then our tree is empty, so we should return false. So if it is not empty, we will check if root that data, or the data of our root, is equals to data. If it is true, then we should return true. So this means that our data was found inside our binary search tree. Else, if root.data is greater than data, so if the data of our root is greater than our data, then we should check inside our left child, since the left child will always be lesser than the root node. So we will recursively call the search helper and pass in the left child as the root, and we will pass the same data as arguments. Else, if root.data is not greater than data, then we will check inside the right child, since the right child will always be greater than root.data. So we will recursively call search helper and pass in the right child as the root node and the same data. So let's try our search method. So in our main class, we will print the boolean value that search method will return if we will check 6. So as you can see, the search method returned true, since 6 is in our binary search tree. But if we will pass in 0, it will return false, since 0 is not in our binary search tree. So the next method that we should define is the remove method. So this method has void as return type, and it takes one parameter, which is the data that we want to remove from the binary search tree. And just like the other methods, this method needs a helper method. So its return type is node, and we can call it remove helper. This method takes two parameters, which is the root node and the data that we want to remove. So before we call remove helper inside remove method, we should check first if data even exists in our binary search tree. So we can use the search method that we just defined earlier. So if data exists, we can call remove helper, and we can pass in our root node and data as arguments. Else, we can also print that data does not exist or could not be found. So going back to our remove helper, we should check first if our binary search tree is empty. So we can use the same condition. So we should check if root is equals to null. So if root is equals to null, then our binary search tree is empty. So we should return root or the null value. So before we can remove our data from the binary search tree, we should locate it first in our binary search tree. So we should check if data is less than root data. So if data is less than root.data, then we should recursively call remove helper and assign it to the left child, since the left child will always be lesser than the root.data, ay the root node. So we will pass in the left child in the data. Else, if data is greater than root.data, then we can assume that data exists within the right child. So we should recursively call remove helper on right child. So root.right, then we will call remove helper and pass in the right child. Else, if the data has been found, we should consider two conditions, since I have mentioned earlier when creating the node class that a node can be a parent node or a leaf node. A leaf node can't have or don't have children nodes. So if we will remove a leaf node, we can simply assign the root node to null. Else if the data is a parent node, then we will shift the nodes to fill in the gap that the parent node will left behind. So we will start to check if the node is a leaf node. So we can say that a node is a leaf node if the value of its left and right child is null. So we can check if left is equals to null and root.right is also equals to null. If this is true, we can say that the root node is a leaf node or it has no children. So we can just simply assign null value to root. So that way it will delete the data that we are asked to delete from the remove method. So else, if it is not a leaf node, then we will check if it has a right node. If it don't have a right node, then we will check if it has a left node. So we will start by checking if it has a right node. So root.right is not equals to null. If this is true, we will assign the data of the root to the value that successor method will return. So I will explain successor method in a minute. So we will pass in the root as argument. After that, we will recursively call remove helper on the right child. So root.right is equals to remove helper So we will pass in root.right as the root node and root.data as the value that we will remove. So we will define successor method. So in this method, we will assign root to root.right and while root.left is not equals to null, we will perform this line of code in a loop. Then we will return root.data. So if we recall, the right child should always be greater than the root node. So if we will remove a root node or a parent node, then we will check if there is a right node. If there is a right node, we will get the least node in the right child and assign it to the position that the root node will leave behind. So that's why we assign root.data is equals to the data that successor method will return, or the least node of the right child. After that, we will remove that particular least node from the right child, since it has already taken the position of the root node. So that's why we recursively call remove helper, pass in root.right as the root node and root.data as the data that we will remove. So if there is no right child, we can use the same process to get value from the left child and take the position of the root node, but we will invert the values. So we will also use the same method, but we will call it predecessor, since a left child precedes the root node in terms of value, and the right child succeeds the root node in terms of value. So that's why they are called successor and predecessor. So we will invert the values in the predecessor method. So we will take value from the left and we will take the max node. So it is opposite from the right child. So after that, we will return root. So let's try our remove method if it works. So let's try removing 5. So as we can see, 5 was already removed from the binary tree. So let's try to remove 1. So as we can see, 1 was also removed. So let's try 9. So as you can see, 9 was also removed. So what if we will remove a node that doesn't exist from our binary search tree? So what if we will remove 0? So 0 could not be found since 0 was not in our binary search tree. So that is the implementation of binary search tree.